I'm happy to be here talking to you today about resistance and tissue motion. Just want to point out my collaborators here, John Oshinsky. He's actually an engineer like me, but he has expertise in MRI, and I've been collaborating with him for a long time. Ruz Bamini, he's actually instrumental in bringing me to Northeastern University. He used to be at the University of Akron. He's an expert in soft tissue mechanics. And Rafiq Badelia, he is at Harvard Medical School. He's a neuroradiologist, and he was a strong proponent of me coming to Boston, and he's been great collaborating. I'm only 1 mile away from his office, so we've had some good collaborations. And then Daniel Barrow, he's actually at Emory University with John, and he gets us a large number of these images. Again, I'm not mentioning any of my students, but it's a large collaborative team. This picture is probably not needed for this group, since everyone knows CSF and knows what's going on. I really only put it up here so that I could emphasize kind of our group's point of view is that the situation with Chiari malformation is somehow related to resistance, compliance, and tissue motion. I've given talks on various components of this over the years. Unfortunately, I think it's some sort of a conglomerate of all three is the final answer. But today I'm going to focus on resistance, and I'm going to add in some tissue motion. I won't go through all the details of tissue motion, but just to give you kind of the engineer's perspective on how we look at this brain is changing its volume, you know, with this increased amount of blood, and then you can't really say just how it's going to push fluid, you know, in this region. But we talk about it as soon as it goes into this channel. As soon as it goes below the foramen magnum, we say it's a pipe, and therefore we can treat it in terms of pipe flow. But we can't really do anything up above it. All right. So this may not be shocking to everyone, but there's been a lot of talk about cerebellar tonsillar position not being a very good marker for Chiari. Some good papers on that. It's a one-dimensional measurement. It's easy to make that measurement fairly quick for neurosurgeons, but it doesn't really correlate well with symptomatology. And what our thought was is, well, if it's only 1D and you look at something in one plane, this is in the sagittal plane, and you see lots of white space for fluid to travel up and down, but then you look in the axial plane, you see here on the lateral walls, it's really tight. That's why years ago we got excited. We said, we got to have a three-dimensional parameter of this resistance that takes all of that into account. And we do computational fluid dynamics. I'm not going to go into all the details of it. This is a CSF in a subarachnoid space. This is a Chiari case. I'm not going to go through all the details except for maybe the assumptions, which are kind of big assumptions. One is that we're talking about rigid walls, and we know that they're not rigid, right? Because we know that there is compliance in the system. And then also that we're using a static image of moving tissues. We know that the tissue is moving, but yet we take the static MRI and do this careful modeling when in fact the tissue is moving around. The other thing is we're missing nerve roots, arachnoid trabecula, and more specialized things on the inside. So there's a fair number of assumptions involved in that modeling. So what do? We do this computational fluid dynamics, the Navier-Stokes equations, and based on the boundary conditions of flow coming in and out, we can get the pressure at two different locations. So here's the foramen magnum. I pick 25 millimeters down, and then I can get this trace over one cardiac cycle. So that's delta P, but it's not like in steady flow where you just have one number. We get it over a period of time. We can take that and calculate what's called longitudinal impedance. And longitudinal impedance is really just resistance for an unsteady flow. So in other words, I need to take each component of that delta P, break it into its harmonic components, and then divide them out each individually. So I take the first harmonic of the delta P trace and the first harmonic of the Q, take the ratio of that, so on and so on. And
Frank, I've been wanting to ask you this for a couple of weeks. You say harmonics, or you're talking about Fourier transform?
yes.
You're talking about where the big component in your, this is what you're plugging into the equation, the biggest Fourier component.
Yeah, I mean, we do the first 8 harmonics, and that's somewhat of an arbitrary cutoff because we don't think there's a lot of fluid transport for the other harmonics. But and also 25 millimeters is somewhat arbitrary as well. We picked that just because that's where the The tonsil will usually do not descend below 25 millimeters. We did a sensitivity analysis to see if we picked another spot, if it would make a big difference. It doesn't make a big difference.
How do you get the P?
How do you get the P? I didn't go over that, but that's the Navier-Stokes equations, right? So the Navier-Stokes equations relates velocity and pressure. I can explain that. So we've done quite a few papers on that. I want to focus on this paper today that we published last year. And this one I was excited about because I started to work with Dr. Bedelia, and he comes, first of all, one hard thing about doing these analysis is I need really high quality images. I can't just use a clinical scan. It's got to be really, like isotropic, really carefully done segmentation. Well, that's what they do at Harvard on a normal routine. And he said, Frank, you can have my data anytime you want. So he has been working on these headaches, cough-associated headaches, which is like the headache that you get when you cough and then it goes away, say 15 or 20 minutes later, not a continuous headache. So he groups his patients into cough-associated headache and non-cough-associated headache. So then I was like, you already have the groups for me, just blind me, don't tell me anything, we'll do all the simulations and then we'll see what the difference is. So I was pretty excited to see this initially. I'm like, okay, cough-associated headache, average longitudinal impedance, this is my resistance, 1,300. And then non-cough-associated, 300. Wow, this looks like a really good discriminatory tool. And then you look at the tonsillar position and say, well, that's pretty good too. That's 13 here and 9.4 here. Is longitudinal impedance really any better than just looking at the tonsillar position, which I claimed was only 1D, and I went this full 3D. So here's all the data spread out in kind of an interesting plotting form. So on the blue is all the cough-associated headache, and the red is all the non-cough-associated headache. And you can see that the blue is definitely bigger than the red. It doesn't take a calculator to see that. However, you can quickly see that, like say here, 738 for non-cough-associated. If I slide over 738, that's a lot of cough-associated ones that he's larger than. So it's not very specific, right? I'm not for sure which one I would get. So then we went through the, where is it? Oh. So then we plotted, since I have it in this kind of order right here, let's go ahead and plot the tonsillar position in the same kind of, so these are matching up, number one, and see how this, fits out. And there's some surprising numbers in here that I quickly said to my student, are you sure you have the right one? For example, this one right here is that tonsillar position of 7, and yet has a super high longitudinal impedance. And then over here, I got a tonsillar position 24, but I got a relatively low longitudinal impedance. I said, this looks suspect. We need to look at this. And before I go to that, though, let me just plot here the relationship between tonsillar position and longitudinal impedance. So you can see this is definitely, they're definitely related, right? As I go up in tonsillar position, I'm going up in longitudinal impedance, but there are definitely some outliers. Like this guy is that one that I just talked about, that had a 7, and you can see that it varies across the thing. So it's not really perfectly correlated. And here's those specific cases that I was talking about. So this one on the left is the cough-associated headache, 7 millimeters with a high impedance. And this on the right is that 24 millimeter, but with a low impedance. Well, sure enough, if you look in the axial plane, you can see there's very little white space here. So when he segments the thing out, this is really a tight junction here, where surprisingly, even though this guy had a really large descended tonsils, in fact, it wasn't blocking the flow nearly as much. So this would make me excited that our 3D thing is useful. But let's go further to see how useful it is. Well, if we do the area under the curve and try to understand, if we're trying to predict whether someone's cough-associated headache or not cough-associated headache, well, we can do this area under the curve. And if you do it for this new fancy 3D technique, we get 0.77. If we use just the tonsillar position by itself, 0.7. I don't think 0.77 impresses anybody very much. It should be like 0.9 or 0.95 if you're going to have some clinical utility. So we just haven't captured it. Now, the good news is we did a little better than tonsillar position, but not much. They're almost the same. So why is that? Well, so let me review here. So resistance to CSF motion is larger for cough-associated headache. However, there's overlap such that the measurement of resistance is not strongly predictive. So brain tissues are assumed to be rigid for these calculations. Could improve this by incorporating the measurement of tissue motion. We have done a journal paper where we put a tissue motion of the brain at 300 micron, which many of them are more than 300 micron, and we got a 30% difference in longitudinal impedance. So in other words, is it possible that my LI calculation is just not good enough? I need to add in, which we can do. It's more computationally intensive, but we can take the measurements from tissue motion and add it in. I can have my student, he's already dreading doing it, but I already told him we need to do all of them again. So, so we got to add that in and see what the results are. So let me talk a little bit about tissue motion. So about 2015, John Roshinsky called me up and said, hey, I got this new tool for measuring displacement in the brain, and I think you're going to like it. It might be useful for Chiari. Displacement encoding with stimulated echoes, or DENSE. And I got all excited about it. He got excited about it. So what is it? I'm not going to go through the details because I'm not an MR physicist, but essentially we can get the anterior-posterior direction and we can get the caudal-cranial direction so that I could draw little lines that trace out where the brain is. So you can see here, these are just, it's hard to see here, but these are little loops that I see where the entire brain goes. And we wrote a paper on that in 2018 and showed all the methodology on how to compute these. And there are some disadvantages from PCMR that was discussed this morning. So one disadvantage is towards the end of the cycle, you lose signal strength. So we're really only getting 2/3 of the cycle rather than the entire complete cycle. Here's a picture of the motion, and you can see the sort of the smoothness of the data, and you can see that it's primary in the lower part. We showed that the displacement is really cerebellum and brainstem and all this other stuff up here. It moves a little bit, but it's really inside the noise of the measurement. So we published 2 papers on this last year, and we were pretty excited about these papers. One paper, we made the cover of Radiology. I've never made the cover of any journal before. And then in the same year, we made the cover of Annals of Biomedical Engineering. So 2 covers in 1 year really surprised us. And I'm not going to go over all of the data, but in short, this one is comparing to healthy controls to Chiari. I'll go over those results a little bit. And this one is showing before and after surgery. This one here in the middle I slipped in here was 2 years ago. This is a study we did on the accuracy of DENSE. So there was a study to look at the accuracy of DENSE for large motions such as cardiac, but there was nothing for really small motions in the brain. So we built an MRI compatible model that essentially was a small shelf that moved up and down a couple of millimeters, and we went to the grocery store and asked them for a giant block of bologna, 2 inches thick, 5 inches high, and 14 inches long. And then we moved that piece of bologna up and down in a very controlled motion, and we showed that DENSE is accurate to somewhere around 20 microns for a non-invasive, and that's during a cycle. So that's not just one measure, that's over the cardiac cycle, it's at 20 microns. It's a phenomenal tool, and I think that's why it made these covers, I'm pretty sure. So what did we find? I'm just going to give a quick summary here. So here on the left is the Chiari, and here on the right is the healthy controls. So the color coding is 400 micron here. So these can go over 400 micron. We just picked that color coding so you can see the distribution. And you can see that it's not uniform at all, right? I mean, we clearly have more motion on the Chiari than we do on the healthy control. And if you look at the results, if I take the spatial average of the maximum displacement, which gets confusing to say, so the most motion during a cardiac cycle, I take that value and then I average it with each other voxel in there. So if you look at those numbers for the Chiari, we get, for the brainstem, I get 212. For the control, I get 125. So not quite double, but definitely more. And then the cerebellum, 154 versus 73. So that one is double, but just barely. But if I take a little circle and I float the circle all the way around the thing and just ask what is the maximum value wherever I put that circle, sort of like a floating region of interest to try and find the maximum. So this actually ends up being the maximum average within the circle. This is that location. These are the locations where it ended up. Then we get a pretty big difference. Now you're talking Chiari 325 versus 156, so it's more than double. and the cerebellum is 399, 126. So it's like 3.5 times. Not a big difference, but definitely more. So we can take this data, since we have the spatial displacements, and Ruzbe-Amini taught us how to compute the tissue strain within that segment. So here are the strains. Now, the first thing you should notice here is that it's noisier. Why is it noisier? Well, when you take the derivative, you always increase the noise. When you integrate, you get less noise. So we had to do some smoothing to the data that's described in the journal paper in order to not have crazy results here. So you can see pretty quickly that there's a lot of blue and white here, and then you get some kind of red peaks here and there. And so this is compression, this is extension for the Chiari, this is compression and extension for the healthy control. If we go to the results here, I've highlighted in purple the ones that had a p-value. So the brainstem didn't really have a difference in compression between the healthy controls and Chiaris. But the cerebellum did, 0.9 to 0.52. So it's not quite double. And the same thing was true on extension, 0.7 and 0.64, not significant, and here 0.72 and 0.45. So what do we take from that? It's really tiny strain, less than 1%. And these numbers go up if I do that little region of interest circle as well, but I'm not showing all that. But it's different, but it's very small. So brain tissue motion is approximately twice that of healthy controls. Brain tissue strain is approximately twice that of healthy controls, but only for the cerebellum. The magnitude of the strain is small. Unclear if this would cause biomechanical damage that could lead to symptoms. Decompression surgery altered the brain motion and strained back to nearly those values. I didn't show those results, but in that other paper, we show that it comes back to it. But when we wrote that first paper of the post-surgery, we did the analysis with CCOS scores, and it was not correlated with the motion. In other words, you couldn't predict if the patient was going to do well or not. So is tissue motion magnitude correlated with symptoms and or COS? No. But it was a small sample value, N of 21. We have now, in our latest group, we have asked a lot more questions, a lot more detail. So I'm hoping that something comes out of it. But to be honest, I'm not absolutely confident that it will. It's possible that the strain is just so small. I mean, that's why I say here, makes sense in a way. 1%, how can such small strain? So I asked Marcus earlier, if I take my head and I do this like this, what strain am I putting on my brain just by doing that? I would say probably 3, 4, 5%. So this type of strain is really, really quite small. So then we asked, is the tissue motion an indicator of tightness, such that large brain motion would occur in a more severe blockage? So I did all this stuff with resistance, and I have all this stuff with motion. I need to merge the two together. So that's what I have my student working on the last 9 months. I'll tell you the answer right away. The answer is no, they're not related, but I'm going to show you. So here's the Chiari. So he did the same thing. This is longitudinal impedance for the Chiaris, longitudinal impedance for the controls. In this particular case, it's quite a bit more gentle blockage than the cases from Harvard. These are not really that high, going up to only up to 500. And here is a kind of a complicated plot, but I'm going to walk you through it. So let's just focus on the top plot here. So this is brainstem, max brainstem displacement, and then longitudinal impedance. If the tightness is causing a pressure environment that would cause the brain to move, then I should expect, if I've got a really tight, high impedance, then this thing should have more motion. And you can see the p-values are listed over here, but I think you can see by eye, this is just all over the place. The blue dots are the Chiari malformation cases, and the red dots are the healthy controls. But neither one of them is going hand in hand. So I don't really know what's driving the brain motion. And the same thing was true for the cerebellum. You can see here it's just kind of all over the place. Maybe a little bit of a trend, but generally speaking, they're two independent things. I've got tightness, and then I've got motion. They seem to be two independent quantities. So in conclusion, image processing and engineering analysis identified several unique characteristics of Chiari. I feel like I've been saying that for years. I keep identifying things, but they don't connect with symptomatology. It's really kind of tough on my lab. We need to link these symptoms to the biomechanical characteristics in order to have clinical decisions. What's the root cause of these symptoms? Are altered biomechanics important or just a side effect? I've been working on this for years. Does biomechanics, it looks like it should play a role. When you look at the image, you say, oh man, that's tight. Oh man, that's moving a lot, whatever. It makes sense. But why is it that some patients have a tonsil position of 20 millimeters and don't have a lot of symptoms? Another patient has 5 millimeters and they have a lot of symptoms. So we don't know the answer to that. So our next step is to do just what I said, is to compute this resistance with the patient-specific tissue motion. And my student is gearing up psychologically to try and do that. I think that's going to be probably a 9-month process. And then I'll be improving the accuracy of the resistance calculation yet again. But I hope the next time I come back to you, I say, oh, I found it. But my confidence is not high. We'll see. Thank you very much for your attention.